Okay, hello. We are going to start chapter 11. This chapter is about covariance and correlation. So it's a little different from what we have done in the past, like 4 or 5 chapters. Okay. Um, so let's review what we have done in chapter 3 and 4. In those chapters, we learned measures of location and measures of variability, right? So, simply speaking, the mean and the variance capture the center, where the center of the data is, and the variance, the standard deviation, range, interquartile range, these kind of measures capture how much data are scattered or distant from the center, right? These are two measures, summary measures we considered in chapter 3 and 4. But those measures are only about one variable. When you have a single variable, these two types of measures are pretty much like good enough to explain what is going on in many cases. However, what I'm going to consider here is we will consider more than a variable. So suppose there are two variables. Then it is still possible to calculate the mean and the variance for each of those variables, right? However, the problem is the relationship is not captured by the covariance, like by the mean and the variance, right? The mean and the variance is only about each of the variables, but their relationship requires something else. That's what we are going to do in this chapter and in the following chapter. So this chapter we are going to study the covariance and the correlation coefficient. These are new summary measures that we are going to study. And in the next chapter, we will study the regression model. So regression is actually the ultimate goal of this course. So you are going to use the regression in other advanced economics courses. So we learned everything to learn the regression. So that is coming in the next chapter. Okay, so let me start with kind of absurd example. So climate and economy, are they related? So yeah, it's an absurd question. So economically does not make much sense. But let's think about that, because I intentionally brought this because I'm not sure what is the relationship. You don't know how their relationship would be. So what I'm going to do here is I have real data on 183 countries, and I have their average yearly temperature in Celsius and GDP per capita. So can you imagine, would these be related or not? So like, for example, colder countries are richer or poorer. I'm not certain. So we will study how we can do it in this slide, in this chapter. So the data is from 2012. So you can I will also share the Excel file on Brightspace. So this is some observations from the data ranging from the richest country. Qatar is the wealthiest country, and Luxembourg, Macau, Singapore, Kuwait are ranked highest in terms of their GDP per capita. And also we observe their temperature. Actually, Qatar, Macau, Singapore, Kuwait are pretty hot countries in hot climate zone. But Luxembourg is maybe the only country among these top 5 that is cooler than the others. So anyhow, so let's see, then are they related or not? There will be more than 100 countries below there. So we have to look at the overall pattern. So top 5 countries do not give us any specific information about the variables. So on the horizontal axis, I put temperature. So hot countries here, colder countries here. You see, Canada and Russia are on average minus Celsius in terms of Celsius. The average temperature is negative. And on the vertical axis, I put GDP per capita. So the higher, the richer. Okay. And then like 1 point, as you know, 1 point is one country. I have 183 countries. So there are a total of 183 countries on this plane, XY plane. Okay. So for example, Qatar is the highest, like wealthiest country among our data in our data. So Qatar is at the highest point. Luxembourg, Macau, Singapore, and maybe this must be Kuwait and Norway. USA is here. Canada, Russia, you know. So there must be a lot of hot and poor countries here, like that. This is called the scatter plot. We scatter the countries on their location to their location given by those two variables, right? Their coordinate is determined by those two variables, so we can see their location, their rank, their place easily in one image. So two variables are depicted in one image. So it is very useful to see the relationship between these two variables. And here, okay, what do we want to do? Scatter plot is good, but still, do you see any pattern? It's hard to see. What I can say here is, okay, so there are a lot of countries in this area. Okay, but is there any tendency? It's not certain. So to answer that question, we need to answer decompose the question first. What we want to answer in this kind of questions is like in two folds. First, do colder countries have higher GDP per capita? Is it about direction? So whether these two variables have positive or negative relationship. So this question is about the sign, right? So whether it increases or decreases, okay? And second part of the question was like, how strong is the relationship? So we are also curious about that. So how, like, if you know the relationship, how accurate the relationship can explain those the two variables. These are more specific questions, more academic questions we would like to answer, and those two questions are answered by one line. So trend line, I will call this trend line. So if you can draw a straight line that goes across the data, goes in the middle of the data, in some sense, I will explain how the trend line is defined later. But anyhow, suppose that there is a trend line which go through like the average of the patterns. And then first what we see it is decreasing. Slope is decreasing. That means the hotter the temperature is, the lower the GDP per capita is. So the tendency is negative. The relationship is negative. That's the direction based on the trend line. That is one thing. And like the relationship between the mean and variance, okay, this is the trend, but also what is missing from the trend is the deviation from the trend. So strength is about the deviation, right? So even though we can draw a trend line, but there are a lot of like outliers, like deviations from those trend. So in that sense, the strength is pretty much weak, right? Right. Even if I know a country is like here has an average temperature 9 degrees Celsius, but Luxembourg is this much high, USA is here, and other countries are below. So the dispersion is pretty big. So in that sense, the strength is weak. Okay. So remember, this is how we analyze the relationship of two variables. So, and by the way, then first, I'd like to declare this disclaimer. This analysis is limited in the sense that we only consider straight line. I will consider a trend line that is straight, right? Right. this can be limited. This is limited in many cases. For example, in reality, like you may see this kind of U-shaped relationship. So it's going down, decreasing at first, and then after a certain point, it goes up again. U-shape, right? So this kind of relationship is not considered here, right? For simplicity, because so if you are interested in that kind of things, I recommend you to come to the graduate school, okay? Or another interesting example would be something like that. It seems like there is no relationship when the x variable is low. X variable is small, it does not affect y. But at a certain point, when x variable exceeds a variable a value, then it starts to positively affect y. So flat and then going up. So it's not straight. Slope changes. In both cases, slope changes. That is possible in many like economic examples, right? Let me give you an example. Like for example, as economy develops, like when economy is not well developed, the environment is good. But as a country is developing economically, then at the beginning, it will make a lot of pollution, so environment will go down. But after a certain economic level, it takes care of environment, so environment will get better. Something like that. That makes sense. Another example here, like say government debt. Government debt, when it is low enough, it does not affect anything. It's okay. Having enough like a good level of debt is good, but when the debt is beyond a certain point that they can handled by the government, the country, then that will negatively affect the country. So this is another example. Like say, for example, y-axis is interest rate, and when debt is low, it has nothing to do with the interest rate. But when debt increases too much, then the government's interest rate will increase a lot. By the way, anyhow, they are important, but I'm not going to handle for simplicity. So I will only consider linear relationship. So always the trend is assumed to be linear. Okay. So then, under that assumption, so let me reiterate what I explained. The direction of the relationship is about the slope. So in this case, in these three examples, the first figure shows a downward sloping relationship. So negative relationship. As x increases, y tends to decrease, right? And on the right side, it is positive relationship. As it increases, x increases, y will increase together. They move together, right? But in the middle, there is no clear trend. I would say the trend is flat, right? If you draw a trend line, it will be flat. That means there is no relationship. When x increases, the average of y does not increase at all. Like its center is always here around 4. So in this case, the relationship is 0, right? So negative, 0, positive, it's like sine, okay? Another dimension is the strength. So even if the slope is the same, so the direction is the same, but in these two examples, they contrast the difference in the strength of the relationship. So clearly, the right-hand side example has a stronger relationship. So if you know the trend, the single individual observations do not deviate that much, right? So you can better predict what is going on. But on the left-hand side, it's much more deviation. There are much more deviations overall, and so there are something more than the trend. So the trend exists, but that cannot explain as much as the right-hand side example. So that is about the strength. Okay, so I want you to connect what we are looking to the academic question we can define, like strength or direction. So then what I'm going to do here is we are going to quantify these measures. That is the goal of this chapter. We are going to quantify, make a measure, design a numerical measure that captures first the direction of the relationship. So first we are looking at the direction. And simple idea is, as I said, the direction is to answer when x increases whether y increases or decreases. When x increases, does y decrease or increase? What is the tendency? To quantify that, I will start from the center. Center is their averages, right? So you can calculate the average of x, average of y. In this example, numerical example, 4 and 4, the center, two-dimensional center in the two-dimensional plane is the averages, the pair of averages. And what I'm going to consider is I will divide the observations into 4 groups, right? First quadrant, second quadrant, third quadrant, fourth quadrant. So what I'm going, by doing that, what I have here is, so on the first quadrant, x, the observations, like for example here, has higher value than x bar, average of x. So x increased from its average to the positive side. But at the same time, it's y, this value, this observation has y value greater than the average of y. So also y, average of y increased from its average to this point. So both x and y increased relative to their respective average. So that is the observations in the first quadrant. First quadrant have both increase in x and y. But in the second quadrant, as you see, it's all the observations are right side of x bar. So x increased from its average. So right, x dimension is horizontal dimension. X has increased from its average, but y has decreased. So in this quadrant, x increased but y decreased. So the first quadrant, x, y moved together, but second quadrant, x and y moved the opposite direction. Similarly, third quadrant, x and y both decreased. And fourth quadrant, x decreased but y increased. So then, like in an extreme case, if all the observations are in the first quadrant and the third quadrant, then it is easy to say that the relationship is always positive. They always move together in the same direction. If they increase or decrease, if one increases, the other increases. If the other decreases, if one decreases, then the other decreases. Like that. So they're moving, the two variables move in the same direction if all the observations are in the first and the third quadrant. But of course, there are, like this, there are usually the observations scatter around all 4 quadrants. So you cannot simply say it is increase positive or negative. There are some observations that imply negative relationship. So to quantify that, what we are going to do here is we are interested in the pair of the signs, right? Right here, the first quadrant both are positive, and this is negative. And here positive, positive. So to quantify that, the best way to take the relationship is by taking products like this, right? So x is greater than x bar, y is greater than the y bar. Then their deviation, x deviation is positive, y deviation is positive. So if you multiply them, the product is also positive. Like here, x deviation is negative, y deviation is negative. So if you multiply them, the product will be positive. Minus times minus is positive. So positive. So first and third quadrants will have positive cross product of deviations. Okay? But here in the second quadrant, x deviation is positive, y deviation is negative. Here, x is negative, y is positive. In both quadrants, if you multiply two deviations, the resulting sign will be negative because one is positive and the other is negative. Okay, so we are going to use cross product of deviations to see whether it is on the positive side or negative side, right? So it's this way or that way. That is captured by the cross product. But and then we need to summarize those cross products. So we have in here, we have 183 observations. So we can calculate 183 cross products, right? So we are going to take the average and we'll see which side dominates, right? So if positive side dominates, the average will be positive. If negative side dominates, the the average will be negative. So that is defined as the covariance. So we denote covariance like this: COV of two variables. Always you have to include two variables, right? Because covariance is about relationship. And so x deviation multiplied by y deviation, and sum and divide by sample size. But here we use sample formula because the denominator is n-1, right? You remember when we learned the variance, there were two formulas, sample version and population version. It is about the denominator, whether it is n-1 or n. Right? Same idea holds here. When you use n-1, your covariance, sample covariance, your covariance calculate, the covariance you calculate is unbiased. But when you use simple like n instead of n-1, then your covariance estimator will be biased. Is lower than, it's underestimating the true covariance. But both are used. I think sample covariance formula is more commonly used, so I use that here. Okay. The idea is clear. Just this much is average, and this much is multiplication of deviations of two variables. So, and then compare this. This is variance formula, sample version. And if y equals x, actually y was another variable, same as x. And then this will be x deviation times x deviation, which will be square. Then it will comes down to variance. So variance can be understood as a covariance between x and x itself, right? So this is so in that sense, it is a generalization of one variable analysis. So we are generalizing the one variable analysis to a pair of variables. Okay, so we define covariance here. In the next video, I will give you a simple numerical example to apply the covariance and study some properties of the covariance. Okay, thank you for watching. See you later. Bye.